Today's video deals with sequences. What we're going to do is look at an exploration dealing with patterns and try to describe the pattern and write a rule for the pattern. Then we're going to get into what a basic sequence is. Then next we're going to look at arithmetic sequences. And then finally, we're going to look at geometric sequences. So we're going to take a look at the exploration first, as you see here on the screen. It is about finding patterns. So what we're going to do is describe a pattern for each of the sequences listed below. And then we're supposed to use the description to write a formula for the nth term of the sequence. So when you look at these, some of these may be a little bit more difficult. And so the way I'm going to describe them is based off of practice of looking for patterns. Of course, when you first look at something like this pattern, for example, this one is very easy to identify because to get from the first term to the second term, you multiply by 1/2, and then the second to the third term, you also multiply by 1/2. So we can clearly describe the pattern as multiplying by 1/2. And so now we got to use the fact that we're multiplying by 1/2 to write a sequence. It does require some knowledge of number theory. And so if you look at this, this is really 1/1, and this is 1/2, 1/4, 1/8, 1/16. And so you know these are powers of 2. And so because these powers are 2, we are going to write that as 2 to the power of n-1. And you notice in your numerator, all of those are 1s. So that's the function that is the formula that will describe the nth term of the sequence. Okay. Now, if you come over here to the right, we have another sequence. As you can see here, we're multiplying by 1/2, and then 1/3, and then 1/4, and 1/5. So the way we can describe this pattern, based on the way you see it, is multiplying by 1/n. And then we'll say that n starts at 2, 3, 4, etc. Okay. Now the formula is a little bit more complex to come up with, but I will tell you that in the numerator, it's a 1. It's always going to be a 1. And down here, it's going to be n factorial. You're probably asking, what is n factorial? You'll learn more about n factorial later. Okay. The next pattern is dealing with 10 to the first, 10 to the, and then 10/1, 10/3, 10/6, 10/10, and so on. Okay, so what you can say here is this is multiplying by, actually what's happening is our denominators, we're adding to get to our denominator from this number to this number, we're adding 2, and then from here to here, we're adding 3, then add 4, add 5, and so on. Okay, so we can describe that pattern as adding n plus 1 to the denominator, where n starts with 1, 2, and so on. Okay, the formula for this is given as f of n is 10 over n times n plus 1 all divided by 2, which will simplify to f of n equals 20 over n times n plus 1. Again, some of these formulas are very challenging to come up with. I don't know if you are familiar with these numbers. These numbers in the denominator are called the triangular numbers. It's a pattern developed from geometry. I want to go back to this sequence here. This is actually multiplying by n plus 1, 1 over n plus 1, and n starts at 1, 2, 3, 4. N starts at 1, 8, counts up. So 1, 2, 3, etc. Okay, our fourth sequence, you have 1 over 4, then 4 over 9, 9 over 16, 16 over 25, 25 over 36. As you can see, all of these numbers are perfect squares. This numerator starts with the first perfect square, a non-zero perfect square, rather, which is 1, and then it goes to the next one, 4, 9, 16. Okay, so I can describe this sequence as fractions composed of consecutive perfect squares. And so the formula we can use is n over n plus 1, but then we have to square it. So you can square this, and then you square the denominator as well. And then the last sequence, these are fractions. We have 3 over 7, 5 over 10, 7 over 13, and so on. So we can describe this pattern as the numerator increases by 2, and denominator increases by 3. And so the formula for the nth term, these are all one more than an even number. So this is 1 more than 2. This is 1 more than 4, 1 more than 6, and so on. So we can write it as 2n plus 1. These are down here. These are actually 4 more than a multiple of 3. So this will be 3n plus 4. Okay. Now, again, with this exploration, we're just looking here and identifying different types of patterns for each types of these sequences of numbers. Okay. So that leads us into sequences. What is a sequence? A sequence is a list of numbers, as you see here on the screen. So, for example, 3, 5, 7, 9, where the first number is called the first term or element or member, and then the second number is the second term, and the third number is the third term, and so on. And then the dots just tells us that the sequence goes on forever. Okay, we have we have different types of sequences. We have something called a finite sequence. Okay, a finite sequence has domain for the finite set. For some finite set 1 through n for some natural number n. In other words, it's just a list of numbers that stops at a certain number in the sequence, whereas an infinite sequence has the domain 1, 2, 3, etc., which is all the sets of natural numbers. So we'll be dealing more so with infinite sequences in this video. And so we're going to start with some examples. So we're going to talk about how to write terms of a sequence. And so the sequence given here is an equals 2n plus 1. and they want us to find the first 4 terms of the sequence. So all you're doing is starting with n equals 1. So you're going to plug in 1 for n and compute what the first term is. So plugging in 1 gives us 3. You're going to compute the second term by plugging in 2, gives us 5. And then you're going to plug in 3. That gives us 7. And then you plug in 4, and that gives us 9. And there are the first 4 terms of the sequence: 3, 5, 7, and 9. The first 4 terms. Our next problem is a little bit more complex sequence. They want the first 4 terms of an equals 2 plus -1 to the n over n. So the same principle, we start with n equals 1 and plug in. So when you simplify that, you get 1, because 2 plus -1 to the first power is -1. So 2 minus 1 is 1 over 1 is 1. Second term, so we have 2 plus 1, because -1 squared is +1. So 2 plus 1 is 3 over 2 is 3 over 2. Our second term. Our third term is 2 plus -1 to the third power over 3. So that will be 1 over 3. And then our fourth term is 2 plus -1 to the power of 4 over 4, which is going to be 3 over 4. And so those are our first 4 terms of this sequence. We have 1, 3 halves, third, 3 fourths. There we go. So if you understood these problems, you should be able to do those practice problems as well. Okay. Now we move on to something called a recursive sequence. So what a recursive sequence is a sequence that uses its current terms to get the next term of the sequence. And so you may have heard about the familiar Fibonacci sequence. So the Fibonacci sequence follows this characteristic of a recursive sequence. And so the first 2 terms of the Fibonacci sequence, as you see here, or listed over here, are 1s. And to get the next term, you add the previous 2 terms together to get the next term. So if you notice here, 1 plus 1 is 2. And then to get the fourth term, so 2 is the third term of the sequence. To get the fourth term, you will add 2 and 1, that gives you 3. And then to get the fifth term, you add 3 and 2 to get 5, and so on. Okay. So again, a recursive sequence uses the terms, it uses its current terms to get the next term of the sequence. So we're going to do an example of a recursive sequence. They want us to find the first 5 terms of this sequence. And they tell us that the first term of the sequence already is 1. And the formula for the recursion is AK plus 1 equals AK plus 1 for K greater than or equal to 1. All right. So here, our first term is already 6. Okay. So the first of 5 terms is 6. To get the next term, A2, all right, we take 6 and add 1 to it. That's basically what the sequence says. So 6 plus 1 equals 7. So that's our second term. Our third term, is 7 plus 1, and that's equal to 8. Our fourth term is 8 plus 1, and that's 9. And then our fifth term is 9 plus 1, which is 10. So here are our first 5 terms of the recursive sequence: 6, 7, 8, 9, 10. Those are the first 5 terms of this recursive sequence. Okay, if you understood that problem, here's this problem for you can do on your own. So our next, the next thing we're going to talk about is arithmetic sequences. So we're going to talk about how to develop a formula for an arithmetic sequence. So the following sequence you see here on the screen is arithmetic: 7, 11, 15, and 19, etc. The first part of this exploration says, what is the common difference between each term? Justify your answer. So the common difference is when you subtract any 2 terms, what do you get? So the common difference would be 4. More so positive 4. And how do I know that? Because 11 minus 7 is 4. 15 minus 11 is 4. 19 minus 15 is 4. And that keeps going. Okay. That's the first part. The second part says, write an expression for each of the following terms by using the first term and the common difference. So here, I'm going to use the first term, which is 7, plus 4 times, I need 0. Well, really, I need 4 times 0, and the only way I can get 4 times 0 is 1 minus 1. And you'll understand why I use the 1 in a moment. The next term will be 7 plus 4 times 2 minus 1. A3 is 7 plus 4 times 3 minus 1. A4 is 7 plus 4 times 4 minus 1. A5 is 7 plus 4 times 5 minus 1. And A6 is 7 plus 4 times 6 minus 1. Okay? So now, if you actually work these out, you'll get each term. So 7 plus 4 times 0 gives you the 7. 7 plus 4 times 1 gives you 11. 7 plus 4 times 2, that gives you 15. 7 plus 4 times 5 gives you, I'm sorry, 4 times 4. 7 plus 4 times 3 gives you 19, and so on. So now we're going to use what we wrote in part 2 to write a formula for the nth term of the sequence. So we know that an, the nth term, 7 is our first term, so that will be considered a1, plus 4, that's our common difference, we'll call that d. And then these are n, that's each of these are n, and they keep changing, so that's n minus 1. So that is the formula for the nth term of a sequence based on what we have here. And now they want us to tell us now they want us to describe what type of function is an, and they want us to justify our answer. So if you really look at this, we're adding the same thing each time. And that behaves the same way as a linear function. Because if you remember, a linear function, you're always adding or subtracting the same thing, which is considered the constant rate of change. So an is a linear function because the common difference is the rate of change. Okay? So now with that said, we can now talk about what an arithmetic sequence is. So this is an arithmetic sequence. I have two examples here. An arithmetic sequence could be a sequence where you're adding the same number, or you can have an arithmetic sequence you're subtracting the same number. Okay? And the formula for arithmetic sequence is what we developed in the exploration just a few minutes ago. Okay, I'm just going to put a 1 here. And notice that the formula is written slightly different, but it's still the same thing. Okay, so in order to write the formula for the nth term of an arithmetic sequence, we need the first term and we need the common difference. As long as we have those two, we can write those. So this is considered an explicit formula because it tells us exactly how to get it. This right here is an implicit formula, this recursive formula, and it's implicit because it requires us to use a previous term to get the next term. Okay, so with that said, pay attention to these formulas here. So in recursive form, to get the next term, we just add the common difference, which is normally what we're coming up with or describing the pattern anyway in words. Okay, so here's an example. So consider the following arithmetic sequence, 4, 9, 14. So it's asking us for the common difference, and then for the next 4 terms, and then the explicit formula for the nth term, and then the implicit formula. Okay, well, the common difference is going to be 9 minus 4, which is 5. So our common difference is 5. The next 4 terms, all we're doing is adding 5 to get the next 4 terms. So the next 4 terms would be 19, 24, 29, and 34. Three, we want the explicit formula for the nth term. So remember the explicit form is an equals a1 plus d times n minus 1. And so we need a1 and d. So our formula is an equals 4 plus 5 times n minus 1. Okay, and then the fourth part wants the implicit formula for the nth term. So it's an equals an minus 1 plus d, but we do require that n to be greater than or equal to 2, because if n is 1, that puts us at a0, and we don't technically have a0. And plus, that is a contradiction of the definition of arithmetic sequence or any type of sequence dealing with the domain, which is the set of natural numbers. So natural numbers starts with 1, 2, 3, 4, etc. So an here would be an minus 1 plus our common difference, which is 5, or n greater than or equal to 2. And you have to say the restriction on n, or it's going to be implied. You can just start plugging in any value of n. Okay, so if you understood that, then you'll be able to do this example here. All right. And so the last thing we're going to talk about is developing a formula for a geometric sequence. Here's a geometric sequence here, 2, 4, 8, 16. They want to know what the common ratio is. What is the common ratio between each term? And we're supposed to justify our answer. So a ratio is, of course, a fraction, and you're dividing two things into each other. So as you can see here, the common ratio is 2. And how do I justify that? Well, if I take 4 divided by 2, I get 2. If I take 8 divided by 4, I get 2. If I take 16 divided by 8, I get 2, etc. So if I keep doing that for every consecutive term, I will get the common ratio of 2. So now it says write an expression for each of the following terms using the first term in the common ratio. So here I want 2, yes? So I want 2, and then I got to use this 2 here. Well, if I'm multiplying, I can't multiply by 0 because 2 times 0 is 0. I need this to be a 1 when I finish. So my exponent has to be 0. So it's going to be 1 minus 1. And then for this one, it'll be 2 times 2 to the power of 2 minus 1. And then the next term is 2 times 3 minus 1. The next one is 2 times 4 minus 1. The next one is 2 times 5 minus 1. The next one is 2 times 2 to the power of 6 minus 1. All right. Now you should be able to see a pattern here because that's going to help us with part 3. It says use the expressions you wrote in part 2 to write a formula for AN, the nth term of the geometric sequence, and then we're supposed to describe what type of function it is, and we're supposed to justify our answer. Well, if you notice here, AN deals with the first term, so it's A1. And then this is our common ratio. We're going to call that R. And then if you notice with our exponent, we're always taking 1 away. So that's R to the power of n minus 1. And that will be the formula for a geometric sequence. And then we need to describe what type of function it is. Well, we're multiplying by the same number every time. So that is indicative of an exponential function. So AN is an exponential function. Because the common ratio is the common base. Okay, the common base, and the base is just this number here. So let me clarify that this 2 is not necessarily the same as that 2 there, just to help you out here. Okay, so with that said, we can now talk about what a geometric sequence is. So a geometric sequence is a sequence of numbers in which the terms are multiplied by a common ratio R to get the next term. So here we got 2, 4, 8, 16, 32. And so each of these numbers multiply by 2 to get the next term. So a geometric sequence has a common ratio. Here's the formula. We developed it before. So that's A1. And just like the arithmetic sequence, we need A1 and R in order to write the formula for the nth term. So this is called our explicit formula. And this over here is called our implicit formula. For the recursive sequence, notice that for the recursive sequence, we're multiplying the previous term by R to get the next term. Okay, so with that said, we can do our final example here. We have 3, 12, 48. So this is asking for the common ratio, then the next 4 terms, then an explicit formula for the nth term, and then an implicit formula for the nth term. So our common ratio would be 12 divided by 3, and that gives you 4. And if you want to convince yourself it's 4, take 48 divided by 12, and that gives you 4. The next 4 terms are as follows. So multiplying 48 times 3 gives us 192. Then the next term is 768. and the next one is 3,072, and then lastly, 12,288. Those are our next four terms. So next part wants the explicit formula for the nth term. That's given as an equals a1 times r to the n minus 1. So here our a1 is 3 and our r is 4. So our explicit formula for the nth term of the sequence is 3 times 4 to the power of n minus 1. And 4, we want the implicit formula for the nth term. So that's given as an equals an minus 1 times r. And we need n to be greater than or equal to 2. So our implicit formula for an is 4 times an minus 1 for n greater than or equal to 2. And that is our last example for this video. Here is the practice problems that we have here. I want you to take note of the fact that we have a negative term in here, so that's going to make the work more interesting as far as finding the next four terms and the common difference. So this concludes the video on sequences, and thank you. You have a great afternoon.